So, what is geometry? Well, the word geometry can be split into the roots geo, which is from the Greek for earth, and metry, which is from the Greek for measurement. And indeed, geometry as a subject originated from our need to measure things on Earth or to measure things we are used to experiencing in the world. So, you've probably already learned some basic geometry motivated by this practical need. Like, you know how to measure the length of this snake, or how to calculate the area of this picture frame, or how to calculate the volume of this box. Well, much of the geometry you know at this point is based on intuition. That is, it's based on stuff that just seems or feels to be true. You haven't really learned how to explain exactly why it's true. For example, here are two triangles. They seem to somehow be the same in some way. Here's another triangle. It's flipped, but still it's in some way the same as those first two. This triangle here is also the same to the first three in some way, but not quite in the same way. It's like the first three triangles, but larger. Now here are two more triangles, and compared to the first ones up top, there's something just different about them. Notice that you don't really know how to explain exactly what it is about these triangles or why these triangles are the same or different. So even if you know the terms congruent and similar, like if you know that we would call these first three triangles congruent, and compared to these first three triangles, we would say this fourth one is similar to them, even if you know those terms, you don't know how to explain why they're congruent or similar. So again, what you have right now is intuition. You have a sense of what seems or feels to be true. What you don't have is what mathematicians call rigor. Now, rigor is basically just the concept of solidly explaining why things are the way they are on a firm, logical basis. In Chapter 2, you'll be introduced to a method called proofs of bringing rigor into your ideas. Through proofs, you'll be able to solidly and logically explain why some things that seem true are in fact true. Now, intuition versus rigor applies to all of math, not just geometry. So let's go back to talking more about geometry in particular. Geometry has, of course, been around for a long time because even humans in ancient times were able to observe things in the world and felt the need to measure things or to figure out the relationship between different shapes and such. Well, around 300 BC, there was a Greek mathematician from Alexandria, Egypt. So here's where ancient and modern-day Egypt was and is. And this cross marks where the city of Alexandria is. Well, around 300 BC, there was a Greek mathematician from Alexandria named Euclid. This is just how you write his name in Greek. Well, Euclid tried to take things a step further, and he tried to bring a little more rigor to the things he observed. So to do this, Euclid wrote a book called Elements, and in Elements, he tried to solidly explain why the things he observed were true based on a firm logical foundation. It's important to note that the geometry he wrote about in this book were based on things he and all humans, just like us, observed in the real world. So because of his role in more solidly explaining the geometry of the world as we experience it, the geometry you'll be learning about is called Euclidean geometry. In Euclidean geometry, there are three undefined terms that we'll use in order to make different objects, shapes, etc. These undefined terms are point, line, and plane. They're undefined because most people intuitively understand what they are, and because we can't really explain exactly what they are. A point is just what it sounds like. It's a point. We denote points with single capital letters, and we represent points with dots like this. Note that points do not have size. So even though maybe this point P I've drawn here has a width or height of several millimeters, that's just the representation. The actual point which it represents is an idealized object which does not have any size. Line is also just what it sounds like. It looks like this. would denote lines with single lowercase letters or by two of the points on the line. So for example, if we know points A, B, and C are on this line, we could call this line line AB, line AC, line BC, line BA, line CA, or line CB. Notice that these are just different ways of naming the same line. Again, even though this thing we've drawn here has a fraction of a millimeter width, lines in geometry are an idealized object with no width. Also, note that we often represent lines with arrows at both ends. This is because lines go on forever. They do not have length. That is, this actual line here will keep extending on and on off of your computer screen in both directions. So suppose we have a line L here, and suppose we have points x and y, and I tell you that x and y are on the same so-called level as line L. Are points x and y on line L? Well, the answer is yes, because lines go on forever. So even though I only drew this much of line L here, it keeps going on through x in this direction and through y in this direction. The last undefined term is plane. A plane is a sort of flat sheet, which we denote by single capital letters or by at least 3 of the points on the plane. So if we know points A, B, and C are on this plane, we could call this plane ABC, BCA, etc. Again, in geometry, a plane is an idealized object, so it doesn't have any thickness. For example, a flat piece of paper could represent a plane, but even though the paper itself has thickness, the plane which it represents does not. Furthermore, planes do not have edges, so even though I might represent a plane like this, these 4 edges there are just there in order for us to draw it. The actual plane does not have these edges, so the actual plane goes on beyond these edges. An example would be, suppose you're in a room, and suppose you place a piece of paper flat on the floor, and you say this piece of paper represents some plane, say plane M. Then since the plane does not have edges, you'll notice that your flat floor represents the same plane. So suppose if we have a point P on the floor, since the piece of paper and the floor represent the exact same plane, plane M, P is on plane M. So I could very well delete these edges of the paper here and say plane M is represented by the surface of your floor. Now, your floor presumably has edges, but again, the plane does not. It just keeps going on past these edges. Given these undefined terms, we'll be following in Euclid's footsteps, and we'll try to rigorously explain why things that seem true are true. To do this, we use 3 important things: definitions, postulates, and theorems. These 3 things, definitions, postulates, and theorems, are essentially the building blocks of geometry.